Hi everyone, my name is Aarya Pandey and this is a walkthrough of my final year computer science project, a credit card fraud detection system that combines machine learning, explainability, and a demonstrative web interface built in Flask. The project takes a real world challenge to build a model that can detect fraudulent transactions while also remain easily interpretable to the user. Uh, I've divided this video into three chapters. Chapter one would be the machine learning bit, how the machine learning models were trained, what processes they go through, and how the Kaggle data set was used to train and test them on certain instincts. The second chapter would be more about the front end, how these models, when they're stored, how are they called on to by the front end, what does the front end do with them, and what is their purpose there. While the last chapter would be how the front end compares and talks itself with the database, where these models can also go and retrain themselves, essentially. Enough chit chat, let's get into the machine learning bit. I will be sharing my screen, and the next thing we will watch is the Python notebook. There you go. So here's my Jupyter notebook, and as you can clearly see, the first cell is full of imports. NumPy and pandas is something we use for data modeling. Matplot and Seaborn is something we would use to visualize data, whereas sklearn metrics is here to help us create a confusion matrix to better explain what our models have done so far. Like I said, we got the database, we got the data set itself from Kaggle.com. It is a completely anonymized data set. We know this because A, it was written while I downloaded the data set, and B, because as you can see, columns V1 all the way through V28 technically are quite uh, unknown to us. This is done on purpose because Kaggle and the European Cardholder Union, I'm assuming, did not want private informations of cardholders to be out on the internet. This works in our favor because there's no ethical concerns for us when we attempt to do something with a dataset like this. The only two classes that we know about are amount and class. Uh, the class column has a binary input. It is either 1 or 0, 1 being a fraudulent transaction and 0 being a non-fraudulent transaction. Amount is basically the amount that they might have spent on that card. This is an important field because from what I read, amount is the only column that they did not transform. All others but amount and class went through something known as a PCA transformation. A PCA transformation would make the data look something like this. It is basically there to convert and easily view the data for a machine and not for a human. If only you could see, yep. This is something I was just being cautious about. There are no missing imports, there are no missing elements within the database itself. So again, that works in our favor. And here we are. So this is a visual representation of the class column in the data set. As you can see, the one down here is barely visible, whereas the zero is a towering building. This is because there are 99.83% transactions that are non-fraudulent. And so for someone like us who would want to develop something based on a fraudulent transaction anomaly, we only have 0.17% of all records to play with. Uh, I don't remember exactly, but I believe that the total number of transactions for this data set was somewhere around 284,704. And the only fraudulent transactions within all of those were about 398-ish, maybe 400. No more than 400 for sure. So, because we knew that the amount is not transformed, we've used scalar fit transform to get it into shape, basically, so that it mingles well with the rest of the database and does not stand out. We will now be splitting the test and the training set. The approach I've used here is an 80-20 approach where 80% of the database is used, data set is used to train the model, and then the 20% is used to test on that trained model. Uh, where were we? Yep. Amount, as you can see, scalar.transform. We've done it two times because, again, one for the test set, one for the train set. And these are, again, just visualizations of each column. This was done when I was just starting out with the project. I wanted to know how each column and its data uh, link to each other or speak to each other within a single column. The shape here is a very good normal curve shape, which means they have been transformed well. Something like this is a much worse transformation when you compare it to something like a V25. But anyway, moving on. Uh, Model building on imbalance data. So the approach I've taken here is to use two models, logistic regression and XGBoost. What I've done is I've trained these models on three different types of the same data. First, we use the imbalance data set. So the raw data set that we got from Kaggle, we just split that into an 80-20 bit and prepare these models, train them on it, and see what the outcome is, which we will soon. The second approach that I've taken is to undersample the data. When you undersample the data, it basically means there will be an equal number of fraud and non-fraud classes with priorities given to the fraud classes. So what I mean to say is if there are 400 fraud classes, let's say, there can only be 400 non-fraud classes as well. Yeah. Oversampling, on the other hand, is a completely different thing. It is literally the opposite. Synthetic minority oversampling technique, or SMOT, is something that I use to oversample my data. What that did is basically it synthetically created as many fraud classes for the number of non-fraud classes. So undersampling with going down and still remaining at a 50-50 ratio, while oversampling with going up while remaining at a 50-50 ratio. To break this, I also wanted to try doing it on an imbalanced data just to see how the models would truly perform. So let's get into it. Here's the logistic regression training model. As you can see, we're first finding an ideal parameter. Hyperparameters are very important when it comes to training machine learning models. We gave the model itself a choice to compare certain C values with the ROC AUC, which is the rate of curve. And the best C was then chosen to be implemented in the final prediction model. This is a very stale version of a confusion matrix, but we will look at a better confusion matrix right at the end of this notebook. Uh, for context, a confusion matrix is basically a square with each side being assigned a true positive or a true negative or a false positive or a false negative. So the way you read it is, okay, top right corner would be true positive. So how many of these records were true and how many of them were fraud and how many of them did the model catch? The second one would be true negatives. How many of them were frauds but the model failed to catch? The third one would be a false positive, where it is not really a fraudulent transaction, but the model did capture it as a fraudulent transaction. And again, false negatives, neither a fraud nor was caught. Happy lives. So, as you can see, accuracy of 0.999, sensitivity of 0.65, specificity of 0.99, and an F1 score of 0.76. We do not concern ourselves with accuracy while we do fraud detection or anomaly detection sort of problems. It's because there are so little fraudulent cases to compare to that even if a model on an average says every single transaction that goes through is not a fraud, it will still be 99.9% accurate or 99% accurate at least. We look at sensitivity to know what type of recall does the model have, how many times does it let go, and how many times does it not remember a particular thing. By a particular thing, I mean a fraudulent transaction. How many times can it let go of fraudulent transaction? So the higher the accuracy, obviously, the better. The lower the sensitivity, it could cause some problems. Here we are looking at the ROC curve for the unsampled data. This again is the test set. So yeah, we are expecting a good ROC curve of 98%. But now let's try it on the training set. On a training set, we get a similarly nice score of 0.97, but we need to remember that when we're talking of trillions of dollars, or at least $80 billion that we are predicting that will go away in 2040 just through credit card frauds, even 0.01% of it could be a huge chunk of money. Here is a summary of what we just saw, and now we'll be moving on to the XGBoost algorithms. I'm sorry, I'm going to pick my pace up a bit because there's a 20-minute video limit. Anyway, so XGBoost algorithm, similarly, we tune in our hyperparameters in a range. So we specify our learning rates, we let it choose a subsample, and then train it. If I jump straight to the results, you can see that the training XGBoost model perfectly scored a ROC core of 100%. But see how it drastically changes and drops down by about 10 points when it just tested on the same data, just a version of it that it had not seen. Handling data imbalance. Like I said, undersampling and oversampling are the techniques I use to handle data imbalance. Here is evidence of undersampling where I only have 396 fraudulent and non-fraudulent classes, creating a good 50-50 ratio between the two. Logistic regression similarly trained on specific parameters. Then we get the best C score, train it again on the best C score, but this time we train it on the undersampled model. That's why there's Y train under, and there should be an X train under. There you go. It got an accuracy of 94.5%, which is pretty good. But what is even more impressive is that its F1 score, sensitivity, and specificity are also among the mid to high 90s. The ROC, again, an excellent of 99. But now let's look at what it does when it is actually presented a test set. As you can see, precision for fraud classes has dropped significantly, whereas the ROC curves remains the same. Just to give you a summary, there you go. The test and train set might not look too different. In some cases, it performs better, but in reality, the performance is slightly worse, where it just fizzles off for a while. Okay, so now to XGBoost. Doing the same thing again with XGBoost. I'm just going to skip to the results this time. Uh, on the training set, again, it did end up getting 100 because that is what XGBoosts are known for. They're known for exponentially boosting the gradient within a particular set. ROC curve, again, here is a 0.98, which is not too bad at all. As you can see, the training set, it proved to be brilliant, where it got 100% for everything. Not too bad again on the test set. Similarly, we do the same for synthetic minority oversampling techniques. So we've got about 227,449 records each for fraud and not fraud classes. Logistics mode, if I skip to the results, a test of 99 and a training of 97, sensitivity of 0.9 and 0.92 again could be a little better. Same with the XGBoost. Oops, sorry, I skipped that. Test 100 and training 96. 96 again is not too bad when it comes to XGBoost models. What I've done now is I've used joblib.dump to store each and every one of these models. So this two primary models and then four versions of those two models, so six in total. So there's underbalanced, unbalanced, undersampled, and smart. This goes for both logistic and XGBoost. This joblib.dump would help our front end talk to these guys while they are needed to do some prediction, some calculations out on the front end, right? Remember that these models were trained on a particular data set. So if they're faced with something completely new or something completely out of the blue, It is the job of the front end to stop them, and it is not their responsibility if it is not accurate or precise or sensitive, or yeah, the F1 score isn't enough. Now we'll come a bit lower where we create the confusion matrix. As you can see, I don't know if I can zoom in this. No, I can't. Uh, the top right is a not fraud and fraud combination. So it is basically something that is false, negative, true, negative. Again, very similar concept to the ones we saw. It is just a better visualization tool to use a confusion matrix like this than something else. Uh, these are all just testing. So that brings me to the end of the model. Let's move on to chapter two. Chapter two would be app.py, which is the front end of it all. Again, the front end is purely demonstrative. I know it does not look very pleasing to the eye, and I know it could do so many other things in such a better fashion. But the goal here was to make the models talk to the front end and get a result out of the front end using the models we've trained in a different notebook somewhere else. So to run this, I use a simple command of app.py, which I already have. So let's just move on to the notebook right now. Nice. There we go. So the first screen you come on to is login. Yes, it is a login page. It is quite similar to any other login page out there. Let's register ourselves as a user. Let's say I am red@gmail.com. Oops. Username would be red again. And my password would be my password. And we register ourselves. It gives us a good confirmation message on top. I know it's not very pleasing to the eye, but it gets the job done. Again, we log in now, red@gmail.com, and the password is this. Welcome, Red. So here you get two options to communicate with the models at the back. You can either upload a CSV file as a bunch, so you can have about 50 to 100 records gone through in the same time, where all six models kind of fight and learn and predict fraudulent transactions. Or you could do the same with just a single record if that is what you wish to do. So since we're speaking of single records, while I was making this, entering every single record got really tedious. So I was like, okay, why not just create a pre-fill form function? So you can just choose your credit, single transaction credit called file, right? Which would be in the project folder. Yep, there you go. And you would use a single line file. So yeah, let's just go with sorry, I don't seem to have one here, but no worries, I do have a backup. Yep, there you go. So this is a single transaction file. Of course, I did know it is a valid transaction after I saved it. So I can just upload and pre-fill the form. It pre-fills all your unknown variables. Of course, this could be later changed and modified in future scope to make it compatible with real world variables. And when I submit the transaction, it gives me a true result, which is what it should. Now, if you're worrying about this confidence score here, the confidence score here is for the model being false. So, to put it in a story-like format, logistic unbalanced model says that this is a valid prediction because it has a 0.05% confidence of it being a fraud. So, and the same for the others. Moving back to the dashboard, we will now upload a CSV file. Again, similarly, we can choose our CSV file. This time, I hope I do have. Yep, let's just go with this test mixed sample. Could not get better than this. So this one would run it through both models and all three versions of both the models. So here you get a very similarly placed ROC, AUC values, F1 score, recall precision accuracy. and what model performed better on this particular data set. Also, when you do end up downloading the dataset again, these would be highlighted in red, flagging that they are fraudulent transactions. Not very beautiful to the eye, but it is something that can be implemented in a very good design challenge sort of way. You can download this report as a PDF. It's going to save right to your laptop. It's going to look exactly like this. Yeah, there you go. That's the fraud report. I've downloaded so many of them while testing. And that is all for now. Yeah. So that ends chapter 2. Let's log out of here. Good message to have been logged out. And now let's look at the database. So that's the database that we are using on. Uh, it is a very simple to and fro communication between the front end and the back end. Here, if I refresh, there you go. That's the new person. I've hashed out the password so that no one knows except for the person who is supposed to know the password. And this is the fun bit. So transaction record, every time you upload a single CSV file or a batch CSV file, all transactions are stored here with a unique identifier. The cool thing here is it actually depicts of whether the models there predicted this as a fraud or not, and what was their source of upload. That to me seems like a pretty cool way of retraining my data if I ever have to. And yep, that should be all from the database as well. I know it's not very comprehensive or very in-built, but as a design challenge or as a software engineering challenge that let's make it interpretable as well as machine learning based, I found it to be quite cool. Uh, so my conclusion here would be very, very simple. The project taught me how to more than just code. It taught me how to build like systems. Up until now, we were just building a screen or a very shabby version of a website, so to say. But this is a system that actually starts talking to each other, can be used to retrain. I did try on using SHAP, but unfortunately, my Mac just couldn't agree with me, and the GPU kept breaking. Uh, SHAP is Shapely Added Explanations. It would boost the entire interpretability bit of this project to a completely different level. It will basically show us how each and every fraud model and each and every class column are reacting and talking to each other. I now better understand the importance of the model transparency. I now understand why it is important for a model to be transparent in the first place. But there are certain things I would do differently if I could go back in time. First, I would manage my time better. I spent too long on tweaking the model and making it so perfect that I left all of the other bits just lying scattered around it. That said, I did follow my mentor, Dr. Mark Perry's advice, especially around not making enough time for the system. I mean, I just wanted to go wild with it. He's the one who contained me enough to have something to present right now. Overall, I'm quite proud of what I've built. It's not perfect, but it works. It is a system that is semi-usable. It is not industry ready, but it is a good stepping stone for someone who would want to make something like this for a professional industry using real data, using real transformers, using uh, active real-time fraud detection, prediction, and stuff like that. Yeah. Thank you for watching.